quickly with Chantal will explain, and then we'll go on to lesson 3. But first, are there any questions about playing with models last night? Anyone have any? Was it okay? You didn't? I realised we took back your name tags, and that meant unless you wrote this down, you wouldn't know. But so maybe, when do we close the account? Wasn't that good?
Obviously tonight, so if we stick with it until midnight, I guess.
Yeah, so we'll close it tonight. If you don't have any playing with it, then you can. So write down the details. But also, Chantal will share a link with everyone here, which will have the software. And I'll make some comments as we go through about how you might put that on your own laptop. Basically, everything is free. So, R is free, everything is free, so you can get the software. And our team will continue to develop this software and add new functionality. And you are very welcome to share and use all of that as it develops. As the caveat emptor, you heard that you're not buying, but buyer beware. We're still developing it, so you can't use this without thinking. You must think, and if you find problems, we would very much like to hear about these problems. Okay, so today we're going to deal with sampling. This is getting information. Remember in Bayes, what you want to do is you want to find out about the posterior, the thing that puts together your prior knowledge and what the data tells you in order to say now what your state of knowledge should be. And we can't analytically get and the posterior is a distribution. We often can't analytically solve for that distribution, but what we can do is draw samples from it. And those samples then allow us, by normal statistical descriptive techniques, to understand things about our state of knowledge. The way in which we're going to draw our samples for these evidence accumulation models, we Markov chain Monte Carlo. So this is a sequential technique where you draw a sample of the next one, you draw depends on the one you just got, and some new information. So it has what we call sequential dependencies in it. And in particular, we'll use the differential evolution version of this, which takes care of the problem of, well, it tries to, it's a different problem of posterior correlation, but the fact that the parameters are all strongly linked. And this paper is the one I would recommend that you read. I think also I will share my overheads with you, and these, as you can see, are hot links. You can click on that and you can just get the paper. So very often we have a policy of not only open data and science, but also we just put our papers on the website because we don't really think publishers should give them to the publisher for free. So anyway, so you can get, from my website for instance, you can get all my papers. Sometimes not in the journal form, but you get them. So anyway, this is my colleague and it's on our Newcastle site. So I don't want to spend too much time on this except to say that we have this sequential acquisition and that we need to tune things so that we get a nice fat hairy caterpillar. That this is difficult because of correlation. These two parameters are correlated. If they're uncorrelated, it would be a round sort of thing, but it's a oval, and that indicates correlation. In order to make things work well, we need to understand that correlation structure, but we don't know it. So, and it's very strong in the LBA and in the DEM.
Could you explain more details? A little bit more about
About the the Metropolis Hastings step. This step. Maybe I explain it in the context of the here. So this is the key things we need to know, because some of these things you might have to change occasionally. So our idea is, first you have to make a choice of how many chains. Now, more is probably better. You can never have too many, except that that will be costly. You'll have to compute them. And in particular, the early part of that doesn't say don't remember the early part of the sampling, you're doing what's called burning. These aren't good samples yet. And if you start very wide with lots of chains, that multiplies the amount of wasted samples. So you do want some sort of compromise amount. The recommended minimum is 2 times the number of parameters you're sampling, plus 1, up to 3 times. I think there's a default value in the software, but you can change it easily. With all these R functions, if you look at them, you'll see that there will often be some default values, and then you can just type the argument and change the name. So, number of chains is the first important thing, so there'll be lots of them running around. For each chain, we do the crossover step. The second important second and third potential parameters here are this multiplier, gamma, and this perturbation term, eta. This size of this thing, if this is big, then the new thing has big influence and where you were before has small influence. So this will cause the update to be large. If you make it small, it causes the update to be small. So there is some compromise there. The standard value is there, and that's for reasons of, if you assume a particular type of model, that's optimal. So notice it scales with the number of dimensions. As you have more dimensions, you want to be more conservative in your steps. Life gets complicated in high dimensions. That will mean that this is smaller. You can also simply, if you think about this one, this is an alternative one. I think in the software, in hierarchical, I put this one on, and in the subject level stuff you're doing today, I put this one. I don't think it makes a lot of difference, to be frank. It's only when things go bad, this is where you may play. It's a potential, place that might help. This one is a uniform between a half and 1. And so you can see that if this was 1, then the influence of the change equals the influence of the original. And if it's half as much. And that gives you a sense of the scale. Typically this would be a number less than 1. Here you can see that it's less than 1 for D equal to 3. The square root of 6, 2 by 3 out of the square root of 6 is less than 1. This one, the perturbation term, just needs to be there and small. And the only place it can go wrong is if your parameters happen to be even smaller. And that can happen, right? You may have a region where you're sampling something that's between 10 to the minus 6 and 10 to the minus 4. And so setting this at 10 to the minus 3, as is the default, would be a bad choice because it would cause big jumps relative to the scale of the parameters. So typically all right, but something to think about. Now, the Metropolis Hastings step, just forget, I think it's a Metropolis step, isn't it? You remember it's Metropolis step if it's symmetric, and it's Metropolis Hastings if it's asymmetric. This is that term symmetry is about the jumping kernel, the way you jump. If the jumping distribution is such that going forward and back is symmetric, then some extra terms drop out, and we call this the Metropolis algorithm. If it's asymmetric, then it's the Metropolis Hastings algorithm. So I describe the Metropolis step here. It's a quite intuitive idea. What you do is you say, here's how good I am now. You assess your likelihood for the point you're at. And your aim is to go to better places in general. So you want a rule that tends to accept things if it gets better. So then you choose another one. You say, how good is this point? If it's better, you always accept it. If it's worse, you can still accept it, but with diminishing probability as it gets worse and worse. And that's encapsulated in this equation. So alpha is the probability of jumping. This is the ratio of the probability of the new thing on the probability of the old thing. If the new thing is bigger than the old thing, then the minimum of 1 and something greater than 1 is 1. So you always jump. Alpha equals 1. If this is less than that, let's say it's half of that, then alpha is set at a half. That means half the time you accept it, half the time you reject it. If this thing is horrendously bad, and this is almost zero, you'll never go there. So you keep away from bad places, but sometimes you go to maybe not the best places because they can lead you to even better places. That's the intuition. So this is the metropolis Hastings algorithm. And it is quite normal for this to fail to move on some proportion of times. It shouldn't always move. There are some more efficient samplers around, like a Gibbs sampler, which always moves. You need more mathematical knowledge to take a Gibbs step. You need what's called the full condition. And the Gibbs sampler, even if you have it, can fail in highly correlated cases like this. So it can end up moving along a ridge in a way that's very inefficient. So, yeah, is that okay? So I think probably, oops, there's the algorithm, there's migration. I'll just quickly say about migration that the idea is you'll see these chains when we do our sampling, these stuck chains that start in a bad place, and like the swallow that loses contact with the flock, they don't get useful information to rejoin the flock. They're kind of lost. And they may eventually come back, but that could be a very long time. So what instead we do is we kind of do a survival of the fittest thing. We take all of the chains, we move them a little, we perturb them, and then we keep the ones that are good. And that means that these things that are far away are killed and are replaced by a copy, a slightly different copy of one of the chains that's in the middle of the pack, sort of thing, or in the group that's doing well. But the cost of this is that if you do this too often, then something that's good but not the best can take over. It's called a greedy strategy or a winner-takes-all type strategy. And the trouble is that you have a winner who's better than everyone else at this point in time, but is not better than what you could get to. And this is the point of exploration. It's sometimes good to be in places that aren't the best because they lead you to even better places. So if you turn up this migration too high, then you get everything looks lovely and converges, and then much later you see it go and change again. If you're lucky. If you're unlucky, it goes there and you think, I'm converged, everything is good, but you're actually not, so you're fooled. I discovered this because I was using simulated data. So it converged, and I knew it was converged. I looked at it, but it's wrong. Oh, something's wrong. I kept running it, and then it changed into the truth. So, of course, we don't know the truth when we're dealing with real data. So I have a heuristic, which is a guess. It means it's not always right. But 5% is about right for migration. And that's, in all of my tests, I found that's good. What you could do in your application, maybe is different, is do your best to get an estimate, simulate from that estimate, see if you can recover those parameters with your settings. If you can't, your settings might be bad, try changing them, you go round and round, like Baron von Munchausen, and you bootstrap yourself up to the truth, hopefully. The algorithm, that's it. All right, so maybe, Chikara, do you want to talk about this, or do you think it's okay?
所以我们在做那个倍性推论的时候，它其实最简单的概念就是我们要从一些 prior， 然后去导出 posterior， 所以我们有一些 data 在那边，然后我们从那个 data 去 sample 之后，然后知道说我们的 posterior distribution 到底长什么样子，因为我们没有办法一开始就知道事后的几率是什么，但是我们肯定有一些事前的东西，所以我就从这个东西去透过一次一次的抽样，然后去导出它的事后的几率的可能会长什么样子，所以它其实就是一个 sequential sampling 的过程，所以它就是你有一个事前的东西，然后你背上这个抽出来一点的东西之后，然后再背上这个东西，再继续的做这样子的推论，所以就是一直这样的推论的过程。所以它那个 Markov chain Monte Carlo 就是在描述这样子的一个过程的方法。所以你会看到它的参数会 慢慢的移动到某一个地方，那所以我会有一个参数的起始值，然后我就去猜说它后面它可能真正的参数大概长什么样子，所以它就会有跳动的过程。那其实刚刚就有介绍，就是说我们到底是怎么跳动的，所以就有一个 metropolis 的 pasting 的一个语法，那个应该讲说是一个 algorithm 算着，所以你就可以去找那个两个东西的 minimum， 然后决定说你现在该不该跳到下一个地方去，或者是你要停留在原来的地方，还是说你要再跳回来。所以，然后它的 step 就是说，它假如说我现在得到的是1，那我下一次要 move 到1.2，还是1.5，还是2？那你可以做很大的跳动，也可以做小小的跳动。那通常你这样跳来跳去对单一参数的估计是容易的。但是如果说你现在一次要估计100个参数，那你的跳动就会很复杂。所以这个 DEMCMC 就是在解决这样子一个问题，因为它的那个微分的方程是比较困难的，所以现在好像只有 built-in R， 那在做这个东西，那其他的可能比较复杂一点点，可能还没有办法做得到。那所以你就可以看到说我的参数是在移动的过程，然后到最后的事后的几率的那个过程。那你可以看到刚刚有介绍一个是 migration， 所以说我可以从这边，然后慢慢的移动到另外一个地方。那移动到这个地方，你可能收敛了，但是它不是最终的解，所以它还是可能会出现问题。那在这个出现问题的过程当中，那你可能要怎么去解决？可能就是去多尝试一些不同的起始值，或者是多尝试不同的 prior， 然后去看你是不是都可以再收敛在同一个地方。那如果说都收敛在同一个地方，你才可以被说服说这个解可能是我真正要的那个解。那所以类型有没有需要补充的？我大概简单的介绍了。所以我们其实，在做这个 sampling 的过程，只是说我们要怎么去逼近到最终的那个解。那 Bayesian inference 只是它的一个过程，所以大家不要觉得它很困难。那反正所有东西都是电脑会帮你做，那你只要大概了解，就是说我是要从一个大概我猜它是什么，然后到最后它可能是什么的一个这样子的一个过程。对。
Okay, so we're going to work through 5 lessons now. So we'll go to the RStudio, so make sure that you're all logged in, looks like you are. I will work you through some of these by running them, and you can follow along, and then some you can do yourself. So first of all, we'll deal with a single LNR subject. So in other words, simulate out of LNR as one data set and figure out how to get some good samples, which takes a bit of iterative, the word for iterative is going back and forward. We then look at our output and extract the information from the posterior to understand our results. In this case, pretty straightforward in the sense that we know what the parameters were coming in and we're interested in do we get them back. Then I'll get you to work through an analogous lesson, so same sort of thing, but this with LBA in 3.3 and DDM in 3.4, and each of those puts together both of those steps, so sampling and assessing. So sample and assess LBA, sample and assess DDM. We'll probably spend around an hour or so on that. When's our break at? We're straight up just now to lunch.
11:30, yeah.
Okay. And so the last sort of half an hour, I'll go over model selection, which is a DDM example. And I'll sort of explain there are many different model selection things that I work through in detail. It's almost a lecture, but it's written into the script. So you can read along the text and run the commands in one go. And that will probably take us to the end of my section, I think. We probably won't get to hierarchical models. I'd be happy if we get this far. But so you're aware, you'll have the overheads and the software will be there. And there will be lessons that will explain it. I need you may need to give me until the end of the year to get all the hierarchical lessons in good shape. So we'll give you the link, and then, and in fact, Matthew and I and Ishi were talking last night, and for Australian Maths Psych in February, we're running this again, and we'll probably change the structure a little bit. We thought one thing we did badly yesterday was that it was very abstract, the first lesson, so we're going to actually start with a little experiment that you could run on yourself. And collect a little data, and we'll use that experiment structure the whole way through to make it more concrete and real. So that will be in the February one, so you may want to get that and look at that. So instead of abstract things like factors and data, it will be an actual little 2x2 experiment. We think that might help make it clearer. So anyway, we'll keep improving, we'll try it. All right, let's now go to lesson. What that means. Okay. All right. So open up 3.1. So files. We're in tutorial. Go down to 3.1. You can open up all of them if you want. But let's start with 3.1. Alright, now some things are familiar from before. We're using the LNR model. All of this code just goes and gets it, loads it in, puts it back to where we were. I'm going to run a completely new example here, so my numbers won't quite be the same. You should also do the same. So we'll do that, so we get started. Notice too, once you start, a word about when you install this on your machine. R works, when you get R, it's a free environment. I would recommend you also get R Studio, again free, it's just an interface to R that makes it easy to use. Then there are packages that you need, which are things that are contributed by people like me to do certain things. And just be aware that you'll have to install them. So you'll need, for example, for this lesson, snowfall, fall, and this thing that no one can ever pronounce. That's all done for you in this environment. Matthew set this all up with all the packages installed, but you need to do that. And sometimes they're a pain and they don't work with your version of R, and you have to update your version of R and the usual stuff. So there'll be a little bit of pain there. But the packages problems are not our problems. We use them just like you. We can't fix packages for you. We can fix our code, but not their code. All right. Now I'm going to set up a simple 5-parameter LNR model, meaning that I'm
所以我稍微跟各位简介一下那个 R 的那个东西啊。所以你可以看到，就是在这个 R Studio 的 environment 里面有打程式的地方，然后有执行的地方，然后也有你 file 是从哪里来，然后也可以看到它的 plot。那左下方那一块其实就是你现在 working space 里面有的东西，就是你到底有什么资料，所以它都会在左下方那一块呈现。那你可以看到第10行是有 RM 开头的东西，那个就是把你原来的东西都清空，那是一个 function， 是内建的 function。然后再来第13行的地方，它其实就是它把在那个 working directory 里面的东西把它叫出来，然后在第14行的地方，这个是很重要，因为有很多人会贡献他们的程式。那你在启用这个 R 的时候，你需要把你要用的那个程式把它叫出来。所以 LNR.R 就是 Andrew 他们已经发展出来的东西，你就是用这样子的一个 source 的语法把它叫出来。叫出来之后呢，你需要把你的 working directory 重新 set， 你要告诉他你现在在哪里工作，所以这只是一个捷径，就是你把你的路径设好了。那下面的话就是它 model 地方，它是会等于model.DEMC 这个东西，这个是他们已经发展出来在这个 LNR 里面的一个 function， 所以你只是用 model.DEMC 把你要设的那些参数，就是说你要怎么去 specify 你的 model， 然后你哪一些 parameter 你要设成什么样子，然后你可能有一些值你是要固定的，有一些值是你要去 估计它的，那你就把它在这边去把它设定好。那设定好之后，下面其实都是一连串的设定。那设定好之后，它就会告诉你怎么样做 sample，怎么用刚刚的那个 DEMCMC 的方式去做抽样的过程。
Thank you. So we're going to start with a very, very simple model, one that we've looked at before. It has 5 parameters, and we're going to set it up in such a way that the mean of the log normal varies with the match versus mismatch. So does the standard deviation, or at least potentially it could. But we will later choose some parameters to simulate from where it doesn't. We estimate the non-decision time, T0, ST0, the variability of non-decision time, we're going to set to 0 in the constant statement here. The match map is the one we've used before, which just says that stimulus 1 corresponds to response 1 and stimulus 2 to response 2. We have one factor, which is stimulus 1 and stimulus 2. We have a two-choice situation, response 1 and response 2. It's the LNR model.
所以我们这个 model LNR 里面，它有一些设定是需要设定的，所以这是一个5个参数的模型。所以你可以看到在那个list 的地方 p 点 map， 它就把这5个参数去设定了，所以有 mean log， 然后它等于 m 是前面我们昨天讲的在 1.1 的地方有个 match 的那个部分的设定。那它也把那个 SE 就是那个它的 standard deviation 做了一个设定，也是等于 match。那 T0 就是 T0 就是指的是 TER， 就是 non-decision time， 它把它固定成1。然后 ST0 就是它也是把那个 TER 的 standard deviation 固定成1。那后面的部分就是它需要再做一些设定 match 点 map， 就是告诉它左边是左边，右边是右边。然后那个有一个部分就是 constant 的地方，那个地方是不估计的，那个是要把它 fix 在一个定值，所以它把那个 ST0 把它设成等于0，就是把那个部分的地方它把它固定在0，它不去估计它，所以那个是不估计的，但是前面5个参数是要估计的。然后后面就是 factors， 昨天在 1.1 也有教到 factors 是什么 ，response 是什么。然后它现在跑的是 LNR model， 所以最后它的 type 的地方打 LNR， 所以那个 LNR 就是指定说它现在要跑的是 LNR model。
Now we choose a parameter vector to simulate from. We want to make some data up. We are going to choose it so that accuracy is above chance. We do this for the LNR by having a small value for the mean log true and a larger value for mean log false. Although we up here allowed for a difference between the standard deviation for true and false, we will actually set them to be the same, 1, and we will set non-decision time to be 0.2 seconds. So these are important numbers to remember because this is what we want to get back. In other words, in the end, our sampling, when we look at the samples for mean log true, we hope that its mean is -1. We hope that the samples for mean log false has a mean of 0, etc. That is, we recover the truth. Alright? Here we make the data. There is the command that makes the data frame. We're making 10,000 per cell, so 20,000. So we should get this back well. This is better than we can ever do in reality. It's very hard to get a subject to give you 20,000 responses and have them not hit you afterwards. So we are so that's the simulation there. We don't save it as a separate object. We bind it with a model. So data model DMC takes the data created by Simulate, the model that we just made above, puts them all into, I just called it the same object again, data. Okay? Then the final thing that you need for Bayes, so we've specified the likelihood, that's model. We've made data. We also need a prior. I'm going to choose the following prior here. For the mean parameters, I'm going to choose truncated normals, but I'm not going to truncate them, they'll just be normals on an infinite range because mean log can be anything from minus to plus infinity. I'm going to choose gamma distributions for the standard deviations because the standard deviations have to be positive, and the gamma is a positive distribution. Looks a bit like a response time distribution. For T0, I'm going to choose a beta. I'm going to choose a flat distribution. I'm going to choose that between 0.1 seconds. That, because I know, if this really was data, that's a reasonable choice because people shouldn't be responding faster than that. Up to 1 second, that could vary. So if we look here then, T0, gamma, gamma, beta, I have to then give the parameters of all of these distributions. Each of them has 2 parameters. For the mean log, true and false, I'm setting them to the true values. That's cheating a little bit, but you could set them to something different, and as long as it's not crazy different, you'll find your results will be the same. So you should do that as an exercise. Repeat this and change the prior. Don't believe me, check. So you see I've used, in fact here I set SD log to not, the means not to true values. I set them to 2 instead of 1. That won't make a difference in the end because we've got 20,000 data points that will be washed away. And in fact, oh no, wait a minute, that isn't true. I think these are the right values because these are gammas. So I think if you take those and the shape parameter of the gamma, it turns out to be right. You may have lied there. Go look at the prior lessons on wiki gamma to find out about this. I forget the formula for the mean of the gamma. And then T0's a uniform, so 1. And then I've just put all 1s across there because what I'm saying is these 2 normals have standard deviations of 1, these gammas have scales of 1, and the beta has is flat. If I do a 1, 1 beta, it's uniform. So them all being 1 is coincidental. That would normally be the case, or necessarily be the case. Don't be fooled by that. Priors are things you do have to understand and think about. Remember the lessons on priors, draw the graphs. Is this, do you want to talk about this?
Yes. 我再帮大家讲一下，就是说你可以看到 R 的语法哈，就是某一个东西，然后有一个箭头指向那个东西，所以它就是后面的那个东西要把它放到前面的那个变数里面 ，OK 吗？所以你如果想要知道你里面到底做了什么，你其实打前面的那一串，像是 P 点 vector， 你可以直接打 P 点 vector， 你就知道 P 点 vector 到底放了什么东西。所以大家都可以去打打看，就是说你现在喂进去的东西到底是什么，它就产出一个东西在那边。那 P 点你可以看到就是说它这边比较重要，就是说我现在有5个参数的 model。然后我要把这5个参数，我要先给它一些 prior， 就是它的事前几率大概是怎么样子。所以那5个参数呢，它就把它分别给它truncated normal， 就是像是 normal distribution， 但是把它头尾都切掉了，所以它不会从负无限大到无限大，它是从2个值之间把它变normal distribution 去切2个值出来。然后它有 gamma distribution， 有 beta distribution。那我想，如果各位对这些 distribution 没有什么概念的话，可能各位回去要再看一下。那但是呢，你可以记得，就是说他昨天在第1章的时候有讲到，就是说像TER 这个东西，我们要假设它是从一个 uniform distribution 出来的，所以他就选择我现在把它设成 beta distribution， 因为 beta distribution 它是比较平的，所以他把它的参数其实只设在1。所以就会很像是 uniform distribution 的样子。那其他的参数其实它就是把它设成不同的分配的形状。所以昨天我们在那个第2个 lesson 的时候是有教大家，我们给你不同的 distribution， 你大概会长成什么样子。所以我现在就是把这些 prior 设成不同的 distribution， 然后我给它不同的参数的起始值的设定。那这个起始值的设定就在它的大概是在28行到32行这边 P 点 prior 的地方，那大家就可以研究一下它的参数设定，然后怎么把这5个参数给它不同的事前几率的分配。到这边有没有问题？
Okay. So, think of a normal distribution. It has 2 parameters, its mean and its standard deviation. P1 is the mean, P2 is the standard deviation. The gamma has two parameters. P1 is its shape, P2 is its scale. Beta has two parameters. P1 is its first parameter, P2 is its second parameter.
我再帮大家解释一下，因为像常态分配，它有平均数跟标准差这两个参数嘛，对不对？所以它的 P1 就指的是它的平均数 ，P2 就是指的是它的标准差。那 gamma distribution 也有两个参数，一个是 shape， 一个是 scale。shape 就是指的是它的形状 ，scale 就是指的它的大小这样子。那所以 P1 指的是 shape，P2 指的是 scale。那 beta 也有两个参数。 所以它就是把那两个参数做不同的设定，参数设定。到这边可以吗
So you can always, we haven't yet done a full proper help for all of this, but I showed last time, so we will do that. We will provide proper helps at some point. But in the meantime, you can just type the name of the function and you see all of the R. And so, for example, here you can see that T norm, if it's T norm, then we've got the mean and the SD. If you've got the beta, it's shape 1 and shape 2. If it's gamma, it's shape and scale. If it's log normal, it's mean log and SD, or what those P1 and P2 are. So, sorry we haven't yet given full documentation, but you can sort of look at the function. Alright, now we just run all of this. This gets us ready for sampling. So if we want to just highlight all of that and run, this will be all very quick and it's done. All right.
所以大家知道怎么 run 吗？就是你把它选起来之后，然后按 Ctrl Enter， 它就可以 run 了 ，OK 吗？这是最基本的。
Matthew wanted to remind you that as we go through the lesson, both Matthew and Yushin are available. Matthew's not trying to hide because he forgot his hat. He just forgot his hat. So. Now, if you see here, I have comments that help you understand. For example, the first comment says we want to set things up. We're going to make an object called samples, which will be a container for our samples. The way R works is you want to create a container that's got all the holes ready to be filled, and then you fill them. You make the container as you go along is very efficient in R. So first we make that. This is where we have some choices such as number of chains. By default, you can see here that it's 3 times the number of parameters. So if I don't change, so again you could look at this function, and it's a big function with many things in it. But if you look at the top of it, you can see that there are all of its there are all of its options. So there are many, and we will explore some of them as we go. But notice they have default values. For example, thin equals 1, something we'll talk about later a little bit. So it's set at a value that is fine. So I try to set the defaults at sensible things you don't have to change, but you should be aware you can change, you have control. Alright, so we now run this line and we're going to set up an object called samples. Now this has done quite a bit of work. It has first of all made this object which contains all sorts of things. Here are all the things that it contains. It's a list with components. You can actually ask R to tell you what's in it by saying, what are the names of samples? And it will say, samples contains all of these things. Now be careful about just typing samples because it'll try to print them all and some of them are big. But you can look at an individual one. For example, we could type in samples and the dollars operator is the way you look at a component. And notice the way that RStudio helpfully gives you a list of what's in there. So you could go down and, well, let's print a small one like n pars. And we hit enter. And it says that just contains the number 5. So that stores in there that it found it in the models object and put it in there ready to help the sampler. Now, one important one in here is this object theta. We won't type that one because it's big. But what it is an array that contains all of the estimated parameters. So what I'm going to do is do a dim. That tells me how many dimensions the object has. It's a 15 by 5 by 100 array. Why is this? Because there are 15 chains, 5 parameters, and 100 samples I'm going to take. So NMC here is the number of Monte Carlo samples this object can contain. So it's set up ready to collect that. So we're going to now compute 1,500 times 5, 7,500 samples, and they'll all go into their slots in there. Three times. So as Chentar just said, why 15? Because the default is 3 times the number of set parameters, which is 5. That is something that, if you look up here, is set. Get back to it. As a default, n chains equals this thing. That looks complicated, but what that's doing is looking in the model object for the p vector and getting its length and multiplying it by 3. So you can just put in there 20. N dot change equals 20, and you'll get 20 changes. Yeah? So you can change all.
So 所以我们现在要做的是那个蒙地卡罗的那个 sample process。那它已经有一个很好的那个 function 叫做 samples 的 DEMCMC。所以如果你要看这个 function， 你直接打那个问号 function 的名字，它就会把整个 function 在做什么，它就会把它告诉你，然后你就可以看你要怎么做参数设定。所以为什么是15乘以100，对不对？这个东西就是因为你可以去看它的 dimension， 刚刚它有打一个 DIM， 对不对？有看到吗？那它就是去看说我这个 list 里面到底那个我要放的那个 attribute 到底它的维度有多少个？那为什么会是15乘以100呢？是因为我要叫它做100次嘛，那上面那个 DMC 等于100就是100次。那再来就是因为我们有5个参数，然后它的预设值就是做3个 chain， 所以你可以看到那个蒙地卡罗 simulation， 刚刚有个图是像毛毛虫这样子扭来扭去吗？所以你可以设它每一个起始的地方可能是不太一样的，所以它就是做了3次这样子扭来扭去的过程，看它是不是可以 converge 到收敛到同一个最后的估计值。那所以它里面还有很多的设定哦。所以如果说你想要知道它清楚的设定，那你就去看它的方选到底长什么样子，然后你就可以把需要喂的参数把它喂进去。那基本上你要做很简单的，大概这样子就可以了。然后那个它其实这个 samples 最后 output 出来这个 samples 它是一个很大的 list， 你可以看到它里面有很多的向度。如果你只打 samples， 它会给你太多东西。所以如果说你想要看特定一个 attribute 到底是什么东西，你就打那个东西，像是 samples， 然后前号有个 $sign， 然后你要看的那个里面的它的这个东西里面的特殊的向度，像是 theta， 你就打 samples $sign theta， 你就会看到说这个 theta 里面到底装了哪些东西在里面 ，OK 吗？所以你们可以自己玩玩看，试试看。有没有问题？有没有人已经不在了？大家还在吗？还在吗？你要在哦，我解释的非常仔细。我解释的真的很仔细，你问杨立行老师。
Okay. So now I'm showing you what's inside the samples object. So you don't necessarily have to do anything with it. There should be functions to extract and use all this, but I'll give you some insight. So for example, that theta object 15 by 5 by 100, most objects will have names associated with the important things. So you see if you go dim names for that, the 5 parameters, there are their names against them. We will often use a very useful package called CODA, C-O-D-A, to query and look at these objects. So I turn my structure into the CODA structure. And CODA is a general purpose package for looking at Markov chain Monte Carlo outputs. Very beautiful analysis. So I'll convert these forms into that. C-O-D-A. So CODA is